Hello students, welcome to section 5.4, Sum and Difference Formulas. So as we can see here at the very beginning, the sum and difference formulas, the first four, you will be asked to memorize the sine of u plus phi, the sine of u minus phi, cosine of u plus phi, and the cosine of u minus phi. The last two that you see, the tangent of u plus phi, but also the tangent of u minus phi, you don't have to have memorized. As it turns out, there are two other versions of those, though, that will maybe help in that particular process of at least applying in context. As far as these first four again, though, go, we have the sine of an angle u plus another angle v. You're going to be able to rewrite this particular sign of that sum as such: sine of u times cosine of v plus cosine of u times sine of v. Now I've pointed to the plus sign here because the plus sign here is the same as the plus sign there. And then as far as the minus property or part of this formula goes, the property speaks to u minus v. And in the end here you can see there's a minus sign. So sine of u plus v results in sine, cosine, cosine, sine with the same sign. Sine of u minus v, sine, cosine, cosine, sine with again the same sign. I think of the letter S in the word sine, but also in the word same. Same sign here, same sign there. Sine, cosine, cosine, sine. The cosine formula, or version of which you can see here with a plus and a minus. Cosine of u plus v results in cosine, cosine, sine, sine, with a change in signs from plus to minus. And the words cosine and the word change start with the letter C. And think of change, again, changing signs. Cosine of u minus v changes signs, as you can see, to a plus. So cosine, cosine, sine, sine. Notice the first angles are all u, and then v for the first terms respectively, u and then v, as you can see for all. And then u and v for the rest of the formulas that you can see. So again, sine, cosine, cosine, sine, cosine, cosine, sine, sine, to help you remember how that plays out. Maybe you can think of it that way. So the tangent of u plus v and the tangent of u minus v works as follows. Tangent of u plus tangent of v over 1 minus tangent of u times tangent v. And then with the subtraction of the angles u minus v, it's tangent of u minus tangent of v over 1 plus tangent u tangent v. A different version for both that would be something to consider. The sine of u plus v over the cosine of u plus v, but also the other version, as you can see, sine of u minus v over cosine of u minus v. Those are two versions to consider as you're doing this. And then, of course, sine of u plus v, cosine of u plus v can be related back to these two up above, as can the sine of u minus v and cosine of u minus v related back to this second formula and, of course, fourth version or fourth formula. So please take a look at those. You do need to know how to use those in context. Tip: refer to Appendix A in the text for the proofs of these formulas. The sine proofs come from applying the cofunction identities, and the tangent proofs come from applying the quotient identities. The cosine formulas in particular are the ones that they're suggesting you take a look at. And if you want, please take a look at that even before you start your homework as a good reference point. All right, example 1. Find the exact value of the sine of 15 degrees. So we're going to use u and v in context, and in order to do this, we have to rewrite 15 degrees as either a sum of two angles u and v or a difference of two angles u and v. Now be careful. The two angles that you choose for u and v should be angles that you know the sine and or cosine of. So the unit circle is very important to relate back to. For our purposes today, I'll give you a nice head start here. It turns out that the best two angles to use to rewrite 15 degrees into would be 45 for u and 30 for v, such that 45 minus 30, of course, is 15. So the problem, as you're about to see, of course, will be rewritten as such. It'll be the sine of u minus v. So if you consider again up top from the standpoint of sine of u minus v, which is this second formula, it'll be sine, cosine, cosine, sine. Sine, cosine, cosine, sine. So if you put it together appropriately, there you go. Sine of 45, cosine of 30, again that's u and that's v in order, minus, because the sign stays the same, it's still minus here, cosine 45, sine 30. In other words, cosine of u, sine of v. Sine of 45, again, if you relate back nicely to the unit circle, which is something you should do quickly and easily, and you of course get root 2 over 2. Similarly, the cosine of 30, again, unit circle analysis tells us it's root 3 over 2. Cosine of 45, root 2 over 2. Sine of 30, 1/2. So without using a calculator at all, we're going to simplify across, multiplying, so you get root 6 over 4. And then you, of course, on the second fraction there end up with negative or minus root 2 over 4. And then that simplifies as such. So the denominators now being the same, you can subtract numerators such that it's root 6 minus root 2 all over 4. This is the final answer we're looking for as the exact value. Now you can still type this in your graphing calculator maybe and make sure you're in degrees, of course. The sine of 15 degrees as a decimal will be equivalent to this exact value, root 6 minus root 2 all over 4. Please check your answer in decimal form later. All right, example 2. Find the exact value of the cosine of 7 pi over 12. So yet again, we're going to try to consider what this maybe could be rewritten as u plus v or u minus v. So 7 pi over 12, something to consider maybe at first at least is what would this actually look like in radian, or pardon, degree form, since it is in radians. So 7 pi over 12, I'm going to go ahead and convert. And you may remember that when converting from radians to degrees, we multiply by 180 over pi. If you don't remember that, remember though that the pi should cancel in this particular conversion, such that you're left with 180 times 7 all over 12. And if you check that analysis out, you'll end up hopefully with 105 degrees. And because we are getting a fairly nice number, so to speak, 105 isn't terribly nice in the sense that it's on the unit circle, but it is nice because we can think of possibly now two angles that when added or subtracted, particularly on the unit circle, are going to give us 105. And if you think u and v in context, well, how about 60 and 45? Now I will continue this problem in degrees. Technically, you can keep it in radians if you'd like. I don't have a problem with that. In other words, this would be pi over 3, and this would be pi over 4. In the end, your x and y values for those two respective angles should be identical anyways. We're talking about the x and y coordinates of those angles anyways. So, cosine of 60 plus 45, in other words, cosine of u plus v. Again, if we're using the property correctly, from up above, or formula, pardon, it's cosine, cosine, sine, sine. Cosine 60, cosine 45, minus, because again the sign changes from plus to minus, sine 60, sine 45. The cosine of 60 is easy enough, thinking of the unit circle. As is, there it is, a half, as is the cosine of 45, root 2 over 2. The sine of 60, again, not so bad, root 3 over 2. Remember, the y-coordinate is what sine is, while cosine is the x-coordinate of those respective unit circle angles. And lastly, of course, sine of 45, there it is, root 2 over 2. If you do the math across, like before in the last example, root 2 over 4 minus root 6 over 4, as you can see there in the next step. And because our denominators are the same, we can easily combine as such. So your final answer ends up being root 2 minus root 6 all over 4. Yet again, I urge you to check your answer by typing in cosine of 7 pi over 12 on your calculators. If you're in radians, or if you're in degrees, 105 degrees, when you do the cosine of which, you should get this decimal regardless if you're in radians or degrees for that angle or that angle. And the decimal is in fact that. Make sure you leave your answer, however, in exact value form. Example 3, find the exact value of cosine 78, cosine 18 plus sine 78, sine 18. So it appears that u and v are already essentially given to you in the sense that it's already written as cosine, cosine, sine, sine. So with that said, what we'll start the process of, as you can see, noting that u and v are known to be 78 and 18 respectively. So you actually are not denoting the answer given the angle at first, instead of the singular angle as the sum of u plus v or difference of u minus v. You're given u and you're given v in context. So cosine of 78 as u minus 18 there as v, or as easily enough as you can see in the next step, cosine of 60 degrees. And that's easy, of course, because we know that on the unit circle the cosine of 60 degrees is 1/2. All right, moving on. Example 4. Write the tangent of the inverse tangent of -1 minus the inverse tangent of x as an algebraic expression. So what we're going to go ahead and do here, denoting again that from the very beginning here, I'll go back to the top, the tangent of u plus v, but also the tangent of u minus v will most likely be utilized in context. So if I go ahead and assess, looking at things, such that the tangent of this right here, this quantity, we're going to go ahead and denote as u, while this entire quantity here is v. So in essence, we're looking at the tangent of u minus v. And again, if we're thinking about what we did on the very beginning of our discussion, at the very beginning of the notes, we noticed that tangent of u minus v, which no, you don't have to have memorized, but does end up quite nicely as such. When you do tangent of u minus v, you'll have tangent of u, again this whole quantity is u, minus tangent of v, again that whole quantity is v, all over 1 plus tangent of u, tangent of v. Now one thing I do want to highlight, particularly with inverses, but also the trig function of an inverse, or vice versa, we'll also see that with the inverse of a function, is that your properties of inverses will play into things. So it's similar to taking f of f inverse or f inverse of f when we did this last semester. Anyways, it turns out with the numerator in particular, you'll be left with -1, because the resulting quantity is just what you're left with, -1 here, minus, again, here is your other remaining quantity, x. And then in the denominator, 1 plus, as you're about to see, same thing applies. 1 plus -1, and then here just x. So it simply is -1 times x. This then can be simplified accordingly, as you can go ahead and take a look at, where in the numerator it's -1 minus x, in the denominator it's 1 minus x. We can, in fact, maybe take that negative and rewrite it in such a way where it is maybe in the denominator, but I think that fraction is perfectly good. Later on we will revisit inverses and exactly denote or see exactly how it can be denoted, maybe not just by virtue of what you learned last semester with inverses, but technically how it applies to trig functions. Okay, moving forward here. So the next problem, I'll go ahead and uncover what I know u and v to be already, what we can assess. It says verify the cofunction identity sine 90 minus x equals cosine of x. Now the language here is in fact to verify. So we're going to do what we did in prior sections of picking one side of the equation and just working with that to prove that it is in fact equal to the other side. Well, as it turns out, like I've already noted here for you, u is 90, v is x. So this is in fact a sine of u minus v. Because it's the sine of u minus v, here's what we're going to go ahead and take a look at as our first step. Sine u cosine v minus cosine u sine v. So sine 90 cosine of x minus cosine 90 sine of x, which in turn we know sine of 90 to be 1, cosine of 90 to be 0, and of course 0 times anything is 0, so what you're left with, not surprisingly, is just 1 times cosine, and that is a verified identity. We will continue the rest of these examples in class together.